Okay, yesterday we just started to talk about how we can describe the product of two reflections where the lines that those reflections happen in intersect, right? We completely covered the case when those lines are parallel, M and L, and we determined that that's just a translation related to the direct distance between the two lines M and L, namely, it's twice. So yesterday we just got to stating a theorem that creates an analogous set of results about what we can say about the product of two reflections in two different lines when those lines intersect. And namely, it's related to directed angle measurement instead of directed distance. Okay, so let me remind you of the theorem and then quickly go through the steps, the beginning steps that we did yesterday. Okay? So we say if M and L intersect at point C, and the directed angle measure from L to M is theta over 2, then the product of the reflection in M and the reflection in L is just the rotation centered at C through angle measure theta. That is to say, twice the directed angle measure between L and M, right? Much similar to how the translation that we get when we take the product when M and L are parallel is twice the directed distance. Okay? So here's what we did yesterday. I'll draw this diagram quickly. So take a line L and some line M that were given at the beginning from our hypotheses, that is to say, and we'll take their intersection point as C. And the first thing we did was pick some point capital L on the line L, which is different from C. I'll put that out here. L. And then we constructed a circle centered at C, which is not centered at C at all. Let me try it again. That's marginally better. Okay, so we take this circle C sub L and look at the point of intersection with our line M in that circle, and we call that capital M. Right? And then the next thing we did, of course, we're looking at this directed angle measure in our assumption. Right? I'm just choosing to draw this diagram this way, right? Of course, this is also a directed angle measure from L to M. But if you did the homework last night and read page 40, you'll see that these result in the same thing when they're doubled. Okay? We can talk about that tomorrow when we review the homework for Monday when we review the homework for chapters 6 and 7, which I'll give you today and tomorrow. Okay, so the next step, let me remind you, is we'll set L prime equal to the image under the rotation centered at C through angle measure theta of our point L that we chose, right? So that is to say, we're coming, say, up here, and we get L prime, which is rho sub C comma theta. And what we deduced yesterday is that the line M is the perpendicular bisector between the line segment L prime. Okay? Then line M is the perpendicular bisector of the line segment LL prime, which of course, that's just the definition of saying that the reflection in M takes L to L prime, right? Okay. So now let's set J equal to the image under the reflection in L of our point M. Okay, so that is to say, we'll take point M and make it so that L is our perpendicular bisector. J equal to sigma sub L of M. Okay? Okay, which of course means well, just by definition, L is the perpendicular bisector of the line segment MJ. So J is on the circle. And the directed angle from so I want to say from the ray CJ to the ray CM is theta. Okay, so let me just reiterate that. So I have this ray. My notation is getting a little cluttered here. This ray is CJ, and of course this ray is CM, right? And when I say ray, I mean I'm stopping at the point C, or starting at the point C and going on infinitely. It's a half line. All I'm saying is that I come down theta over 2 this direction, right? Or rather, if I start from here, I'm going up positive theta up to this ray, CM. Okay? All right. angle measure theta of j. Okay, so now you can put all this information together. If you remember at the end of yesterday, I told you we're following a general strategy here. We're going to find that these two isometries, reflection in M followed by reflection in L, agree on three non-collinear points with this isometry, rotation centered at C through angle measure theta. Okay, and we've done that. So let me just record all together what we've done. Okay, so all together, this implies sigma M, sigma L of C is equal to sigma M of C is equal to C, right? Because C lies on lowercase l and lowercase m. So reflections in these lines fix C. And of course, we know that rotations fix their center of rotation. Okay? So we almost get that one for free from definition, right? Okay, so what about sigma M, sigma L of J? Well, sigma L of J is just equal to M, right? Where did I get that from? I set J equal to sigma L of M. And since sigma L is an involution, I take sigma L of both sides of this, and I get sigma L of J is equal to M. Okay? Now, of course, M is on the line, little m, so that's fixed, right? And our last deduction was that M is also the image under rotation centered at C through angle measure theta of J. Okay? So sigma M, sigma L of L is equal to sigma M of L, right? Sigma L fixes L because it's on lowercase l. And then we set this to be L prime. But we showed in the beginning that L prime is also the image of rho sub C comma theta of L. Okay, so we've taken, and if you don't believe me that C, J, and L are non-collinear, let's look at this diagram. Okay? They form this blue triangle. So, altogether, now we know these two isometries agree on three non-collinear points. Therefore, they must be the same. So, sigma M, sigma L is equal to rho sub C comma theta. Okay. So, so much similar to our progression in the last case when L and M are parallel, we have all of the analogous results. Okay? So I'll list them here. Okay, so first of all, we have the converse of what we just proved. Every rotation is a product of two reflections. How do I find those two reflections? By which I mean, when I say find those two reflections, what I really mean is to specify the lines about which they reflect, or which they reflect against.
It needs to be lines that C is on.
Okay, good, right, so every rotation has a center. Okay, so you have to pick two lines that intersect at C, that center of rotation.
And have an angle through C of theta over 2.
Right, every rotation comes with a theta, and you want the directed angle measure between these two lines that specify these two reflections to be theta over 2. Okay, so C and theta come from rotation rho sub C comma theta. So basically, pick any line through C, I'll call it L, and then find another line through C with, I guess I should say call it M, with directed angle measure from L to M, theta over 2. It implies that we get rho sub C comma theta is equal to what? Sigma M, sigma L, right? Sigma M, sigma L. The directed angle measure from L to M. That means L comes first when you apply it. Okay? Of course, the situation is entirely symmetric. You could write it in the other order if you wanted to. But as I said it here, this agrees with the choice of terminology that I made here. Okay? Okay. So, that's one. Now, what else do we have? If L, M, and N are concurrent at point C, then there are unique lines P and Q such that I bet if you're looking at your notes from yesterday, you can probably guess what I'm going to say here. Right? If we have sigma m, sigma l, then we can find a unique line sigma n, p, such that this is equal to sigma n sigma p. Okay? And a unique line q, such that sigma q, sigma n is also equal to this. Now, there's one more thing to say here in the statement of this. There's one more condition on p and q. Think about it this way, before I tell you what the condition is. You want all these things to be the same rotation. Okay, sigma m sigma l is a rotation centered at C. Right? So in order for these to both be rotations centered at C, P and Q have to pass through C. Where both P and Q pass through C. Okay, so again, the proof of this is just an example of this. Right? You express sigma m sigma l as some rotation, which we know we can do because there are two lines that pass through C. Then what I'm saying is if there's another line that we know, then we can find a fourth line that also passes through C so that we get the same rotation when we take the directed angle measure from P to M. There's a unique line that makes the directed angle measure from P to M the same theta over 2 that we got from.
Right. There's only one, yeah.
Right, there's only one line.
There's only one preceding line that you're doing from that one here. Line agreed.
Right.
Specific one.
Right. And likewise, the same thing here when I measure in the other direction, from N to Q. Okay? So this is just like the situation when all the lines are parallel and have a common perpendicular. You just have to choose the right distance away. But here, the notion of distance is replaced with directed angle measure. Okay? So, 3. Okay, looks like maybe it's going to be a bad marker day.
Sometimes they make it seem like it makes sense that translations and rotations have the same number of reflections.
Yeah.
Because they behave similarly with minor differences in like the structure that they're set up based on.
Yeah, if you like, when lines are parallel, you're on a circle of infinite radius.
Yeah.
That's one thing. That's one way to say it, maybe, or one way to look at it. And in fact, so what we're going to do when we finish chapter 6, the next thing we'll do is discuss the shared structure of isometries depending on if they're composed of an odd or even number of reflections. Remember, reflections generate the entire group of isometries. So we'll define a useful notion of what the characteristics are of things that are an even, isometries that are a product of an even number of reflections and those that are an odd number of reflections. So Zach's point was, it makes sense because these are composed of the same number of reflections. We'll make that point more precise and expand on that later today, and through tomorrow. Okay, so let's see here. Right. This, again, is just a restatement of something we've already said, but it's useful to write these things down sometimes because different statements make different aspects of the situation more transparent. Any rotation centered at C through angle measured theta is equal to 2 reflections in A and B, where one of A or B is arbitrary line through C, and the other is uniquely determined to have directed angle theta over 2 to the first. Okay, that is to say, I guess really I should say where, let's just say where A is arbitrary, right? Where line A is arbitrary. And B is uniquely determined to have directed angle to A. Of course, you can switch the labels and do the same thing, right? Okay. Okay, one more restatement of our main theorem.
Someone put 3 reflections again.
Sorry?
Just like the 3 reflection one again. Remove the one.
Yeah.
Okay.
Yeah. Right, completely analogous to what we did for a product of 2 reflections resulting in a translation. Or if lines L, M, and N are current at C, then sigma N, sigma M, sigma L is a reflection in a line also concurrent at C. Okay, that goes back to the first equality here. Right? We have a P that's uniquely determined. We just multiply both sides of this equation on the left by sigma n. And then we see that this product of 3 reflections based on lines that are concurrent at the same point must also be a reflection. That would be this sigma p. Okay? All right. So, here's a corollary. A half turn sigma p, capital P, is a product of reflections in any 2 perpendicular lines intersecting at point P. Right? This is just making us recall that a half turn is a rotation by 180 degrees.
Yeah, the angle kind of has to be 90.
So the angle between any 2 lines that you can factor it in into a product of reflections in have to be 90 degrees apart. Has to be half of the angle through which you rotate it, which is 180. Okay. Follows from the fact that sigma sub p is a rotation by 180 degrees. Rho sub p comma 180. Okay. So you'll notice I didn't prove these restatements. I didn't give you formal proofs of this because they're almost identical to what we did in the parallel case. But they're still important to have listed, just so you can use them more easily. You don't want to be stuck on a test and have to derive something that you should have been told. Okay. A product of two reflections is a translation or a rotation. Furthermore, only iota, the identity, is both a reflection and translation.
You mean rotation and translation?
Yeah, I should mean that, shouldn't I? Let's see. Why did I write that? Yeah, I don't know why I wrote that. Good, thank you. Okay, so this is basically just follows from looking at what fixed points, what types of isometries have what types of fixed points, right? So let's just say really quickly. So one, a non-identity translation has no fixed points. Okay. Two, a non-identity rotation has exactly one fixed point. And three, a pair of distinct lines words, these are the only two cases for a product of reflections, right? If you have a product of reflections, either the lines that define them are parallel or intersect. And then the result of that will either have no fixed points or exactly one. Okay? So, this is a step, this is really the primary step in our next goal, which is to classify all isometries that have fixed points of a certain type. This is a special case of that, right? And we want to also classify all isometries which are involutions. Okay, so again, we've talked about all the rotations that are involutions. Okay? So now we want to do that in general for all isometries. Okay? And this might seem kind of mundane, but it really all hinges on our result from last week, or perhaps a week and a half ago, that all isometries are a product of at most 3 reflections, right? So we're well justified in this step-by-step process of what happens when there's 1 reflection, what happens when it's a product of 2 reflections, and now we'll get to a product of 3 reflections. Okay. Sorry?
Can we start with 3?
Yeah, so what I mean is now we'll go back and break that down even further. Okay? We gave some broad characterization. Now we're going to say something more specific. Okay. So. Okay, so here's our first theory. An isometry fixing exactly 1 point is a rotation. I guess I should say i.e. A product of 2 reflections in lines L and M, which intersect. Okay. And isometry with a fixed point, not saying exactly 1, but just having a fixed point, is a rotation or reflection. Okay, so this is immediate from the main theorem of our last section, right? Just restating it this way. So so that it matches with the rest of the things that we're going to say here. Okay, now we're talking about how to classify things based on fixed points, right? But this is, again, just a restatement of the content of what we just did today and yesterday. Okay. So. We also know that, the involuntary isometries are reflections and half-turns. Okay, so this actually takes a little bit more of something to say. Okay. So, let's suppose that we have some isometry alpha, non-identity, such that alpha squared is iota. Then, since it's not the identity, we know there's some point that is not fixed by alpha, right? And alpha of p is equal to q, which is not equal to p. Which, of course, implies that p is equal to alpha squared of p, which is just alpha of q. Okay, so now, since alpha is an isometry, well, remember, isometries are really nice. They preserve all structure that we care about, quote unquote, and they fix certain things, such as midpoints. Okay, so alpha must fix the midpoint of the segment PQ, right? Okay, so what does that mean? This implies that alpha is either a rotation or a reflection. Is a rotation or reflection. Now, we discussed this briefly when we first introduced rotations. The only involuntary rotations are half-turns, right? Are half-turns. So there you have it, exactly what we claimed. Right? I mean, I imagine you might have expected this. But now we have all the classification work out of the way to say that this is in fact the case. That you might be able to conceive of the notion of having something else that is an involution that does not just turn 180 degrees or flip around a line. But in fact, life is actually that boring.
Thank you, isometries.
Right, thanks to isometries. Right. Which is why it's so important that we study their properties, so that we can put results such as this that we believe intuitively to be true on solid theoretical foundation. Okay? Okay. So, furthermore, a non-identity rotation that fixes a line is a half turn. Okay. So,
As long as there's symmetry.
I mean, that's the intuition, right? So let's prove this. All right, so let's say that rho sub c comma theta is a non-identity. Fixing line L. Okay, and let's let M be a line through C perpendicular to L. Okay. Then we'll decompose rho sub c comma theta as a product of two reflections. We'll choose our first line, our arbitrary line, to be n, and then find some unique line n. Okay? I think that was the third characterization I gave you of the facts from the last section, right? Okay? As where n is some unique line intersecting M. Right? Passing through C, I should say. And also passing through C, of course. Intersecting M at C. Okay. So, recall that reflections fix but not pointwise lines perpendicular to the line the reflection is in. Right? Remember this, that a reflection, it pointwise fixes the line that the reflection is in, but then every line that's perpendicular to the line the reflection is in gets flipped, right? The rays get flipped. Okay? Okay, so now let's make a string of computations. So L, by our assumption, is fixed by this rotation, right? That was our first line. We assume that rho fixes L. Okay? So now we've expressed this rotation as the product of two reflections. Okay? So of course we chose M to be perpendicular to the line L and through the point C. Meaning that sigma sub n fixes L. Okay? So this implies that n is equal to L, or n is perpendicular to L. Right. Why is that?
If they're both perpendicular to L, it can't be a rotation.
Wait, I'm sorry. You said n is perpendicular to L?
And
N is perpendicular to L. That's correct. Right.
if they're both perpendicular, it can't be a rotation.
If they're both perpendicular, they can't be intersecting lines which are not the same. Right? So n cannot be perpendicular to L, since n is not equal to m, right? Because these are lines that are distinct, otherwise we would have our rotation be identical. I'd have sigma m here, which would just be iota. Okay? And m intersect at C. So this implies that n is equal to L. Right? So now we have rotations defined by two perpendicular lines that describe our rotation. By our corollary, our last corollary, this must be a rotation of 180 degrees, a half turn. Right? So by the last corollary, and L perpendicular to M. Okay? Okay. So, let's do a couple of examples. And in my mind, the goal of these examples is really to express some geometric notion in an algebraic way to make some deduction. Okay? So, let's say, for example, I were to ask you, first, let's suppose M is parallel to N. How do we find points M and N so that sigma M, sigma N is equal to the product of two half terms? What should we do?
Well, if the second one is two half terms, we know that it's translation.
Right.
Tells us that M and N have to be parallel.
Right. So that's that will result in the right answer, right? So, any other suggestions? Well, first of all, we have two parallel lines. So, if we wanted to go to the definition of directed distance between lines, we could do that. But in order to do that, first we have to specify points on those lines. And how do we do that?
They're also both on the same line that's perpendicular to both M and N.
Yeah. Describe the line that's perpendicular to M and the common perpendicular to lines M and N. Okay? So first, find the common perpendicular to M and N. Let's call it L. Okay? And then we know we'll suggestively call the intersection of L with M, capital M, and L with N, capital N. Okay? And label the intersection with L with M, the point capital M, and L with N, the point capital N. Okay? So, now, instead of explicitly describing the translation, I want to do something a little clever. So, let's just look at this product. Sigma M, sigma N. Here's a silly thing. Did you want to say that? Okay. So this is obviously equal to sigma M iota sigma N. Right? Now, what's a way to express iota? There's lots of ways. There's lots of expressions that compress to iota or reduce to iota, but there's one that's particularly useful to us here. I'll give you a hint, especially if you think about the corollary of how to express a half turn as a product of intersecting lines. What's the condition for which you have a half turn with, that's expressed as a product of reflections in intersecting lines? They have to be perpendicular. Good. So in other words,
So it's like, you know, yeah, or, okay.
okay, so did you want to say that again?
If we're reflecting over L itself twice, then.
Yeah, right. L is a reflection which is an involution. So we can rewrite iota as sigma L sigma L.
Which we know is two half-turns because they're perpendiculars.
Which we know is two after because.
This is perpendiculars pairs.
Yeah, exactly. Because M and L are perpendicular, and L and N are perpendicular.
Those are half-turns at the intersection point, which we just labeled M.
Right. Because we suggestively labeled these M and capital N, we know that the rotations in these two perpendicular lines result in a half turn about capital M. And likewise for here. Okay? So this is equal to sigma M, sigma N. Okay, so I know that we kind of went a long time just collecting facts. But if you really spend time to get comfortable with those facts, you can save yourself a lot of work, right? Or not a lot of work, but some work at least, right? And as I was saying at the beginning, if you wanted to do the translation, you could certainly do that. But yeah, this is a slightly quicker way around. Let's do another similar type of exercise together. Oh yeah, I guess I should say, like, you know, think back to calculus. Think back to like when you were evaluating integrals a lot. This is kind of a common trick. If you think of a clever way to add in 0 or multiply by 1. That's exactly what we've done here. We thought of a clever way to insert the identity so that we can use some other facts. That,
Actually, yeah.
sorry?
Because you want to rewrite it without changing the values, so it's looking for equality.
Right. Yeah, that's the common theme, right? All right, yeah, I agree, Thomas. Thomas says beautiful, honestly. It's a beautiful trick. Okay. So, this one is maybe a little less transparent. Might take a little more time with this one. So, let me ask you, what are the fixed points of the product of rho sub b comma 90 times rho sub a comma 60?
Yes, points.
It's possible that there's only one, right? Okay, why the question?
No, just thinking about it.
Yeah, okay, I mean, that's good.
Yeah.
But you know, if any,
Yeah.
or even if one, right? Okay. So, first of all, so we have 2 points, right? The 2 centers of these rotations.
Are we assuming they're distinct?
Yes. Well, actually, you don't have to, but when they're not distinct,
Oh,
that's a trivial case, right? Because we've talked about how when you have the same center.
you only fix in the center.
Right, okay, so let's say trivially, if A equals B, then this product is just a rotation about about A? And we know rotations only have a single fixed point, your center.
That's because the rotation is not 360 degrees.
Yeah, right.
150.
Yeah, even when you add these, you don't get 150 degrees. Right. But I mean, that's apparent from what we wrote. Good. Good point though. Okay, so this is just a rotation about A, which implies A is the only fixed point. Okay. So instead, let's assume A is not equal to B. So we have two distinct points. I think a good place to start.
Just start by finding a line through both of them.
Yeah, let's make a line through A and B. Okay, so let's just say here's A, and here's B. And let's call this line through A and B L. Okay. So our goal is to find a line M through A with directed angle measure from M to L, half of the rotation that's specified by rho. Okay, so
No, it's M to L? Or L to?
from M to L. Yeah, I think,
You can also find one after it, right?
sorry?
You can also find one after it, and do L to M.
Yeah, that's, if you want to do everything in reverse order, that will get you the same. Yeah. Just a choice of notation that I made in the notes. Okay. So, right. Let me look at my diagram here. Oh, jeez. Sorry, let's make this be over here.
Makes the direction make more sense.
Yeah, this way I can actually draw in the top of the board. Good. Okay. So we want to find a line M such that the directed angle measure, and now, hold on a second. So, right. I want this to be 30. Right?
I think so.
Yeah, I think this is right.
You'll be able to write that as sigma L, sigma M. The row A is 6.
Right. Yeah, good. And we want to do likewise for B. We want a line N through B with a directed angle measure from L to N of 45 degrees, half of the theta from the row that has B as center. Okay, so okay, so this is 45 degrees. Here's my M, here's my N. Okay. So, once I've drawn these lines, or if I wanted to work analytically, I could describe their equations, but there's no need to do that here. So this implies that rows of A, comma 60 is equal to sigma L, sigma M, right? Because I'm going from M to L. Okay, this is where it becomes much clearer to me what direction things should be written in. I'm not so good with visuals. And rows of B, 90, is equal to sigma N, sigma L. Okay? So, now we're basically done, right? We do the same thing as before.
This product does some interesting things.
Say again?
We have a product now where they have an identity.
Yeah, exactly. When we write this product at the end as these two products, what do we get? Well, let me just write that out.
It's the other way around.
Yep. Sorry. Okay, so we get sigma N, sigma L, sigma L, sigma M, or in other words, sigma N, iota, sigma M. So we get sigma N, sigma M. Okay, so based on our investigation, our classification, when we have the product of two reflections that are in intersecting lines, we get a rotation that is reflected about their point of intersection. Okay, so we call this point C. And we're looking for the angle measure from M to N. Right? So what is that?
180 minus 45 minus 30.
Yeah, right. So we just use regular triangle geometry to figure that out. The sum of internal angles of a triangle is 180. So if we just subtract 45 and 30 from 180, we get 105, right? So 105 degrees. So now that means that the directed angle measure from, why did I put it this way? This way, this way, this way. It's the external angle, right?
Yes.
See, I have all my angle measures are oriented.
Yeah.
All my internal angle measures are oriented in the same way.
Yeah.
Okay, so it's this exterior angle. Also, just what we did was prove the exterior angle theorem, right? If you have a triangle and you know these two angles, then you know this exterior angle when you extend, just because you know this angle, and that this has to add up to 180. So it's just the sum of these two angles. Just a theorem of classical geometry. Does it sit well with everybody? Okay. So again, we've expressed our product of rotations as a rotation which has obviously fixed point C.
So why do we express it as rotations?
I'm sorry?
Why do we express it as rotation at the end? Because we know if it's two reflections, it's going to only fix on an intersection point.
Now, why do we express it as a rotation? I think mainly just to show you that it's not that hard to get all the information to specify as a rotation, right? You know,
As like one individual transformation with a fixed point, rather
yeah.
than saying, yeah, we have this array, they're going to fix this one point.
Right, right. You know, it makes things a little more concrete if we actually reduce things as much as possible, right? Okay. All right. So that's the end of chapter 6. So Keenan asks, why isn't the rotation about C, row sub C, column 150? Oh, yeah, you're right. I'm sorry. Right. Thank you, Keenan. This is half the angle that the rotation is. Yeah. Completely correct. I'm sorry for that. 150, right? All important. Remember that, yeah, the angle between lines that specify the rotations that the reflections that a rotation is comprised of is half the angle that the rotation goes through. Right, very good. Sorry about that, and thank you, Keenan. Okay, so here's some homework problems for chapter 6. Okay, so again, I'll announce these on Canvas. And I realized the main fault with my plan to do an extra lecture tomorrow and not have it be required. It's obviously unreasonable for me to have it be required that people show up at that time. What I'm going to do is hold an extra review session on Tuesday night, so that we can have time to address all the homework problems that we might not have time to get to because we'll miss the beginning of that class tomorrow that I'm going to do together. So I'll send out a poll along with the practice exams tonight as to when in Tuesday evening that would be best or suitable for most people, so that we can discuss some of the homework problems that I asked you to do together. Okay? So, and of course, if anybody can't make that, just email me and we can set up a time to do that sometime before the exam. Right, Lynn asks, will there be lecture tomorrow? Yes, I'm going to record a lecture tomorrow and send it out to everybody. And ask that you watch that before Monday. Okay? And I think we'll be able to get far enough. I'm not going to necessarily do a whole hour and 40-minute lecture. I might just do the normal thing, an hour and 10-minute lecture. And then we'll have the makeup time together for discussing the homework problems. Okay? And yeah, of course. If anything is unclear about that, don't worry. I hope to finalize everything and make an announcement tonight. Okay? Okay. So, with that, we can move on to chapter 7, which is where we define the parity of an isometry.
And even an odd power.
Sorry?
We're going to even on powers now.
Say that one more time.
Even on powers now.
Even and odd numbers of reflections. Yeah. Okay. So. Okay. Okay, this is probably going to seem silly or trivial, but we'll soon see the work we have to do to actually put this on a meaningful footing. Okay, so firstly, an isometry that is a product of an even number of reflections is called even. Right? Seems kind of ridiculous that I'm even making this definition, but give me a couple minutes and we'll see why we actually have to be a little careful in our exposition here. So, likewise, isometry that is a product of an odd number of reflections is odd. And finally, this characteristic of an isometry is called, or I should say, this characteristic, what do I mean? Even or odd is called parity. Okay. Now, the word parity usually refers to integers, right? It means whether an integer is even or odd. And it's so ingrained in us when we learn arithmetic that an integer can be neither even nor odd, that the notion of parity is somewhat natural. It doesn't need any justification. However, for an arbitrary isometry, it's completely conceivable that you could have an isometry that is expressible as a product of 3 reflections, that's also expressible as a product of 6 reflections, or a product of some other even number of reflections.
Considering we're using groups, I have a feeling I go for a minimum here.
Go for a minimum what?
Well, number of reflections, but also that I don't think that's how it works here.
Yeah, well, it turns out that's not how it works, but we still have to justify that, right? Okay. So, right, what we have to do is show that an isometry cannot be both even and odd. That it's actually a partition of the set of all isometries. Okay? Okay. So there's some work to do. And I think we can get at least halfway there to showing that this is a well-founded concept for isometries today. Okay, here's a lemma. So if P is a point and A and B lines, then there are lines C and D where C passes through P. So that sigma B, sigma A is equal to sigma D, sigma C. Okay? Notice there's not necessarily any relationship between P and the lines A and B. Okay. So again, we're given two arbitrary lines, A and B. That means that there's two cases we have to consider, right? If A and B are parallel, or if they intersect. Okay, so proof. Let's first assume A and B are parallel. Then let C be the point, I'm sorry, the line, through P that is parallel to A, which of course means it's also parallel to B. Okay? If A and B intersect, say at point capital C, then let little c be the line through C, big C, and P. Okay? So then either A, B, C are all parallel in the first case, or A, B, and C all concurrent at point capital C. So now we just use one of the many statements I gave you
About translations or rotation.
about translations or rotations, right? That's, yeah, the great observation here, right? Is that when you're in the situation when they're all parallel, you can find a unique line such that you have sigma B, sigma A equals sigma C, sigma D, or when they're all concurrent at the same point C, you can say that sigma B, sigma A is equal to sigma D, sigma C for some line D. Okay? And in both cases, we have that sigma B, sigma A, sigma C is equal to sigma D for some line D, which implies our desired result. Sigma B, sigma A is equal to sigma D, sigma C. Okay. So to take a second to point out at this stage, expressed in this form, where I have the product of 3 reflections equaling some other reflection, this does not account for all cases about how 3 lines can interact with one another, right? I have 2 cases here by construction,
Right.
that A, B, and C are all parallel, or they all intersect at the same point.
Versus an example of 2 being parallel intersecting.
Yeah, one pair intersecting, and then the other one not parallel to either of them.
Also possible.
Right. So, this is going to be our main obstacle in finally classifying all isometries.
Happen to have a triangle.
Something like that. Yeah, so that's where we're headed. I just want to point that out because we just barely skirted it here. Okay? All right, so I think we have time for one more theorem. Okay, we're going to start very simply and show that a product of 4 reflections is a product of 2 reflections. And this depends on a couple applications of our lemma. Okay? So, let's take a product of 4 reflections. I'll call this sigma S, sigma R, sigma Q, sigma P. And we'll suppose P is a point on the line little p. Okay? Then, by the lemma, there are lines Q prime and R prime with P lying on Q prime, so that we're just going to take the the middle 2 terms of this product and express them as reflections in Q prime and R prime. Okay? Sigma R sigma Q is equal to sigma R prime sigma Q prime. Okay. Sorry, it's a Q. Kind of looks like an A. So our product of 4 things can be, of course, rewritten this way: sigma S, sigma R prime, sigma Q prime, sigma P. to this time, we'll give we'll use it on sigma s, sigma r prime.
And then P will lie on all except for the last one.
And then what?
P will lie on all except for the last one.
Right. Exactly. We're going to construct it so that there's, in the center, 3 reflections that all have lines that lie on the same point. Or, sorry, intersect the same point. At the same point. They're all concurrent, is what we'll eventually get to in the next 4 minutes. Right. So we have lines, R double prime and M, so that sigma S, sigma R prime is equal to sigma M, sigma R double prime, with P lying on R double prime. Okay, now we just compute. And as Zach noted, I think this is worth writing down. So we have all of P, Q prime, and R double prime concurrent at point P. Okay? So, in other words, can express this as a reflection on some other line, which we'll call L. Which implies that sigma R double prime, sigma Q prime, sigma P is equal to sigma L, or some line L. Okay, so finally, what can we say? We start with our original expression, sigma Q, sigma P, sigma S, sigma R prime, sigma Q prime, sigma P, sigma M, sigma R prime, sigma Q prime, sigma P, sigma M, sigma L. Okay? So just by using that elementary lemma, we have shown that we can reduce a product of 4 reflections into a product of 2 reflections. Okay? So, tomorrow, the first thing we'll do is show that this allows us to reduce any even number of product of reflections into a product of 2 reflections.
It's kind of induction.
Sorry?
It's kind of induction.
Yeah, we're not even going to do it. It's just we'll just say that's true. And then an odd isometry is either a single reflection or a product of 3 reflections. Okay? And then we'll show that an isometry can't be both even and odd. Okay? So, I won't see most of you tomorrow, and that's okay. But I will see you on Monday. And oh yeah, look out for my announcements for the practice material and any other relevant information I said today.
Thank you.
Yep. So Keenan, does this mean that the product of 4 reflections is an isometry since it can be written as a product of 2? Yes. Also, we know that isometries generate reflections generate the group of isometries. So any product of isometries reflections is an isometry. And remember, we had this result that every isometry is the product of at most 3. But now we're getting to the point where it's like, oh, we can say, well, these isometries that are expressible as the product of 2 reflections have certain properties, and then the other ones, single reflections or product of 3 reflections, have other properties. Okay, so that's what the bulk of chapter 7 is about. So yeah, we'll talk a lot more about that tomorrow. All right. Yep. Have a good weekend.